All right, let's talk about lakes. So the first term you need to be familiar with is a term called limnology, and you're going to see this a lot in the geological sciences, and that's the study of lakes. There is a lot of information that we can glean from lakes, and one of the more common things that you're going to see is studies of, say, ecosystems, because they're kind of self-contained ecosystems. You also see a lot of climate studies from lakes, because these closed-off modern lake systems are really good at preserving climate information. And so there's a lot of folks that study lakes. As a sedimentologist or stratigrapher, we're a little more worried about lakes and how they might show up in the rock record, but they all still fall within the wheelhouse of geology. And so we start thinking about, are lakes open or closed system? If you've taken any sort of advanced geology class, you have at least been introduced to the idea of open and closed system behavior. Right? Lakes can exhibit both types of behaviors. So we might talk about a lake as being hydrologically open, which means that the system or the drainage system is flowing into the lake, it is filling up and then spilling out. This is really common in the low mountain lakes. You can think about a small stream spilling into the lake, it fills up, and then it spills out the other end and feeds down ultimately to a larger source. In that case, that lake might have a very consistent water level because this may get us some snow melt, seasonal rainfall, feeds into the lake is kind of almost full, and then it just continues to spill and percolate down through the system. All right, a hydrologically closed system is going to be like a small endorheic basin where the drainages might flow in and there's no output. That's a really good example of a hydrologically closed, where the inflow is less than the outflow and the evaporation. These hydrologically closed systems are really good examples of where we can go in and study things like closed-off ecosystems or climate change. And so there's a lot of folks that study these isolated little lake systems. So a quick breakdown on different types of lakes. Usually we go with three here. We go with the freshwater lake. That's by far the most common. The saline lake, salty water. Those can range from a little bit salty to really salty, which would be hypersaline. And then we have the ephemeral lake, the lake that shows up only during the wet and rainy seasons, disappears during the drier climate times. So with a freshwater lake, it's exactly what it sounds. We have fresh water, but that doesn't necessarily mean that it's open or closed. It can be both. It can be an open system, water flowing in, continually flowing down, can be closed off, as long as the water flowing in does not have a lot of dissolved ions in it. All right. If that closed system does have a lot of ions, right? You think about saline, immediately you think like halite, but it doesn't have to be halite. It can be any number of ions that can form salts. And so when that water makes it down to the basin, evaporation leaves, it starts to concentrate those salts in the lake, and you can get some very interesting mineralogy produced in those saline closed lake systems. Now, ephemeral lakes, those are going to be more common or almost exclusively in really arid environments where you get periodic rainfall, the lake develops, then evaporation takes over and removes the majority of the rain that has fallen in that short period of time. So these are very seasonal lakes. So what drives a lake? What sedimentological forces are at play in a lake system? So we might think about waves, just like on the ocean, but the ocean has a long distance for wind to blow across the surface. What that means, that has a long distance, and wind can blow in a certain direction for a long time, and at really high wind speeds, it can generate large waves, and those large waves are going to cause a lot of sedimentological displacement of all different types of grain sizes, can move just about anything. Now with a lake, even a large lake, the wind doesn't have as much room to blow on that water because they're restricted, they're much smaller. So you don't have as large of a fetch area for the wind to blow across the surface of the lake. The winds can't get going as quickly because they're slowed down when they hit things like the land, right? So the land will slow the wind speed down, trees, any sort of obstruction. And then even if you do get those waves moving around, you've got the shore right there. Just the fact that they're so much smaller kind of limits the impact that waves can play. You can also start thinking about storm events too. When storm events come through, the exact same processes are at play. They can't really stir everything up quite as much. Now the lakes are much shallower than the ocean too. So It doesn't have to be quite as deep for a storm to stir things up. So you have few currents outside of a little bit of wave action, but you can also get some currents because there is stratification in a lake. And it's really cool. So you don't have a lot of currents, so the water's somewhat stagnant. So you get these layers to develop. All right, and the big important thing is called the thermocline. If you've ever been swimming in a lake or even scuba diving in a lake, you know if you dive down not that far, you notice you hit this wall of cold water, right? When you hit that, that is when you have passed beneath the thermocline. You can also get saline differences where you might have really salty water, it's a little denser, sinks down, fresher water's up top. You can get that saline split out of the water, and then you can also get density contrast because of those two things. Colder water is denser, so you can have colder, saltier water down low, warmer, fresher water on top, and that gives you some density contrast. Now you start stirring things around, those can generate some currents that can move sediments. Now the other thing you got going on, since you've blocked off everything, is if you have things dying in the water column, sinking through, they ultimately accumulate in the bottom with no currents, nothing, no influx of water, no outflux. What happens in those deep waters, they're just kind of stagnant, and you can deplete all of that deep water of oxygen. So with no oxygen, you can't break things down. So organic material just kind of gets preserved. And that condition is called anoxia, or lack of oxygen. So what that means is down in these deep lake waters, you can get the preservation of really, really organic rich material. And lakes in a lot of ways work like smaller ocean basins. Everything gets a little bit limited, but you can have a river system flowing into a lake, and when it hits the lake, the energy dies really quickly. You've transported it down to almost a temporary base level, and so you get deposition in the building of, here this is a very good example of a lake delta, right? This little meandering stream is hitting this river, is spilling everything out, and you can see this small little delta starting to form. That sand that it's providing to the lake can then get reworked with some of the wind moving around, the small waves back and forth. You can get fluctuations in the lake level, and it can move that sand around, and that will replenish some of the little sandy beaches that are present along the boundary of the lake. Well, that gets you sand right on the margins, and here you can see on both ends there is a clastic influx on the left and the right. So those are deltas that are spilling in sand along the edges of this lake here. And then the deep water, a little bit of sand gets out there, and that's because you can get these little kind of baby turbidites, lake turbidites. You can also get density currents forming from the water, right? The dense water can kind of start moving around and move stuff around a little bit. These baby turbidites are the same. You just have high sedimentation rates, get a little too steep, you get these kind of underwater landslides, and it gets a little bit of sand, kind of deeper out. But in these deeper portions out here, you're getting almost exclusively very fine-grained mud deposition that's making it way out into the deep basin. In the deep basin, I mean deep for lakes. So lakes are kind of inherently controlled by a very strong seasonality, right? So in spring and early summer, very common to have a lot of outwash because you're melting any snow. Snow's kind of washing through the system. You also generally have rainier conditions in the spring. And what that does is that gives you more sediment, more water. Those are all infilling into the basin. It's replenishing anything in the basin, bringing fresh material in. By late summer, all that is gone. So late summer into the early fall, you get these really stagnant conditions. But biologic activity can go through the roof in these stagnant waters. And so what that means is just real common to get a series of really thin millimeter scale layers where you might get a little bit of clastic material, some fine grain organic material back and forth. And so you'll see these dark light, dark light, dark light bands, and those are called varves. And those are really super common when you can find these lacustrine deposits. But this is what people start studying when they start studying climate change through lakes, because they're usually studying moderately younger lakes, and they can go through and literally, like tree rings, count the varves and go through and do high resolution chemical analysis on some of these to reconstruct conditions through time. So it's almost like a geologist's version of tree rings. These are really common for the lacustrine geologists to be studying if they're trying to reconstruct these paleoclimate records. All right, so that's clastic influx into a lake system. You can also get carbonates. And so the way this works is specifically when you have lakes that either one, don't have a lot of sediment, clastic sediment influx, and have really high biological productivity. Right? Some of these lakes can be very, very rich in biologic productivity, and so that can drive the production of carbonates. You can also get lakes that are hypersaline, or very saline, and that can ultimately lead to carbonate deposition as well. Sometimes they're kind of linked. The fact that it's saline means you only get a handful of species in the lake, and those species just go crazy, and there's so many of them that they can produce a lot of dissolved carbonate in the water, and that precipitates out and gives you the carbonate material. But sometimes you can quite literally just have dissolved carbonates from the dissolution of carbonate in bedrock. In this case here, this is Mono Lake. There's tons of carbonates out here in this lake. This lake is in a volcanic area, and it's driven by the dissolution and mobility of carbonates in the subsurface because of that volcanic system. But you can get both high productivity, high biologic productivity, or it's just dissolution of carbonates nearby. All right, ephemeral lakes. Here's our ephemeral lake system. It's this is Western Australia. They get very little rainfall, and when they do, it pools into these little lakes that are only very temporary. And what you see is you'll see the influx of the rain. Sometimes you'll even see in the sedimentary record raindrops, which is really cool to see because you're looking at an ancient raindrop. And those will fill up and flow around and fill up these small little lakes. And as those lakes evaporate out, you start to pick up mud cracks as everything contracts and dries out. And then you can also start to see evaporites, because as the water is evaporating, it's leaving behind the little crust of the stuff that was dissolved in the water. And so it's really common to see evaporites and mud cracks. Sometimes you'll see these called playas. And so playa lakes is a term that will pop up somewhat frequently in the South America, Central America. You'll hear them called playas. And a really good example of an ephemeral lake here, this is Death Valley. So if you've ever been to Death Valley National Park, there's a place called Badwater Basin. It's the lowest part of the Death Valley area. You're below sea level, very low area. And if you go, depending on time of year, you'll see these small little lakes that have formed from water moving around in the ground, kind of spilling out of these little springs, and it just evaporates before it can go anywhere and it gets stranded. So these are really good examples of ephemeral lakes. If you go on our Geology 360 trip that runs every 4-ish years, we go to Death Valley. Usually there's some water flowing in these. You can see through this picture, there's no water at this time. It's very little sparse amounts of water that you see in these ephemeral lakes. But during the rainy season, or in fact we go in the spring, so snow's melting in the mountains, it's flowing down, and you're getting some water movement there. Late summer, all the snow's gone, and these ephemeral lakes dry right up, and they disappear. And so from a sedimentological standpoint, you see evaporites with these, you see mud cracks, you see periodic flow. Every once in a while you get some raindrops, but they do appear in the rock record because they just kind of keep drying out. They are low spots. And so ultimately, if they get filled in, they get preserved as these small little playa basins.